When the James Webb Space Telescope captured its first deep-field images in the summer of 2022, the astronomers who built it spent decades preparing for what they expected to find. Ancient galaxies, the first stars. The cosmic dawn rendered in infrared light for the first time in human history. They were ready for surprises. Science at the frontier always produces surprises. They were not ready for this. The world got its first look at what JWST could do on July 12, 2022, when NASA released the telescope's first deep-field image at a White House briefing. The image showed a region of sky so small it could be covered by a grain of sand held at arm's length. And within that grain of sky were thousands of galaxies. Galaxies at every stage of development. Galaxies so distant their light had taken billions of years to arrive. The image was immediately described as the deepest infrared view of the universe ever captured, and the emotional response to it was overwhelming. But among the astronomers who spent their careers preparing for this moment, the emotional response was more complicated. Because scattered across that first image and across every deep field that followed were objects that the models had not predicted. The universe at its earliest accessible epoch did not look like the simulations. It did not look like the extrapolation of what Hubble had shown. It looked wrong in ways that were immediately apparent to anyone who knew what they were supposed to be seeing. The wrongness was not subtle, it was systematic. And scattered across every deep field, image practically everywhere, JWST pointed in the sky were small, bright objects that nobody had predicted, nobody had modeled, and nobody could explain. They appeared in enormous numbers. They were compact. They were red. And they existed at a time in the universe's history just a few 100 million years after the Big Bang, when nothing like them was supposed to be possible. Astronomers called them little red dots. It is an informal name, the kind of name scientists give something when they do not yet know what it is and need to call it something before the formal terminology arrives. Little red dots, hundreds of them, distributed across the early universe at a density that made no sense under any existing model of how the cosmos formed. For 3 years, some of the best minds in astrophysics have been trying to figure out what they are. The answer that has emerged from the latest research is stranger than almost anyone expected, and it may change our understanding of how the universe as we know it was built. To understand why the little red dots are so alarming, you need to understand what JWST was built to see and why the early universe is so different from the universe we inhabit today. The James Webb Space Telescope is the most powerful infrared observatory ever constructed. It was launched on Christmas Day 2021 and reached its operational position approximately 1.5 million kilometers from Earth. Its primary mission was to observe the first galaxies, the objects that formed in the first few 100 million years after the Big Bang, when the universe was still young enough that the building blocks of modern cosmic structure were only just beginning to assemble. The reason we need an infrared telescope to see these objects is rooted in the physics of cosmic expansion. Light from the most distant objects in the observable universe has been traveling for so long that the expansion of space has stretched its wavelength. Visible light becomes infrared light. Ultraviolet light becomes visible light. The further back in time you look, the more the light has been redshifted, and the more you need instruments sensitive to longer wavelengths to detect it. JWST's instruments are precisely calibrated for this. It is a time machine pointed at the beginning. What it found at the beginning was not what anyone expected. The first deep field images showed something that immediately unsettled cosmologists. Everywhere JWST looked in the early universe, It found galaxies that were too big, too organized, too present in an era when the standard model of cosmology suggested the universe should still have been a relatively uniform sea of gas, with only the earliest, smallest structures beginning to coalesce. The little red dots were part of this broader shock, but they were not just unexpected in terms of size or maturity. They were unexpected in terms of what they appeared to be entirely. The numbers that emerged from the first systematic surveys were immediately alarming. Astronomers expected to find perhaps a handful of unusual compact objects in the early universe, rare outliers from the standard distribution of early galaxy types. Instead, the first surveys found them everywhere. In the Cosmic Evolution Early Release Science Survey, alone researchers identified hundreds of candidates. Extrapolated across the full sky, the implied population ran into the hundreds of thousands of objects existing in a narrow window of cosmic time between approximately 400 million and 1 billion years after the Big Bang. The redshifts of the confirmed little red dots placed them at look-back times of 12 to 13 billion years. To put that in physical terms, the light JWST is collecting from these objects left them when the universe was between 4 and 8% of its current age. When that light began its journey toward us, the Milky Way did not exist. The Sun did not exist. The Earth would not form for another 8 billion years. The universe at that moment was a place of rapid, violent assembly, where the first large structures were barely beginning to take shape from the primordial gas. And in that violent infant universe, the little red dots were present in numbers that no model had anticipated and no theory had predicted. Here is the problem in precise terms. When astronomers look at the spectrum of light from a distant object, the way it emits light at different wavelengths, that spectrum is a fingerprint. It tells you what the object is made of, how hot it is, how massive it is, whether it contains an active black hole, whether it is forming stars rapidly or slowly. The spectrum is the most fundamental diagnostic tool in observational astronomy. When you look at a galaxy, you know what its spectrum should look like. When you look at a quasar, an active supermassive black hole consuming enormous quantities of gas and radiating across the full electromagnetic spectrum, you know what its spectrum should look like. The little red dots had spectra that matched neither. They were bright, far too bright for their size. They were compact, far smaller than any galaxy with their luminosity had any right to be. Their light was red in a specific way that suggested either a very old stellar population, a heavily dust-obscured active black hole, or something else entirely. They emitted broad hydrogen emission lines that would normally indicate the presence of a supermassive black hole consuming gas at high speed. But they did not emit the X-ray radiation that is the unmistakable signature of an active supermassive black hole. And the black holes implied by their brightness would have been so massive relative to their host galaxies that they violated the established relationships between black hole mass and galaxy mass that hold across every other object in the observable universe. They looked too massive to be young galaxies. They looked wrong to be active black holes. They vanished from JWST's view around 2 billion years into the universe's history as completely as they appeared, as if whatever they were had stopped existing or transformed into something else. The leading theories at the time of their discovery split into two camps. The stellar interpretation held that the little red dots were extremely compact early galaxies, packed with massive young stars, with the red color coming from dust reddening and the luminosity from intense star formation. The black hole interpretation held that they were active galactic nuclei, supermassive black holes consuming gas at their centers, but shrouded in such dense material that the X-rays were absorbed before they could escape. Neither interpretation worked cleanly. Both had problems. Both required the objects to have properties that did not quite match any known class of astronomical object. The 3 years between their discovery and the research that finally identified them were a period of genuine scientific uncertainty that played out in public in a way that rarely happens in observational astronomy. Research groups at institutions across the world published competing analyses. Preprints appeared and were challenged within days. International conferences dedicated entire sessions to the question. Astronomers who had spent decades studying active black holes argued with astronomers who had spent decades studying star-forming galaxies, and neither camp could produce an interpretation that accounted for all the observations simultaneously. The specific observations that proved most difficult to reconcile were threefold. First, the absence of X-ray emission. Active supermassive black holes consuming gas at high rates are among the brightest X-ray sources in the universe. The little red dots produced almost none. Stacking analyses combining the X-ray data from hundreds of objects to increase sensitivity found X-ray emission far below what any conventional active black hole model predicted. Second, the implied black hole masses. The broad emission lines in little red dot spectra, if interpreted through standard black hole mass estimators, suggested black holes of hundreds of millions to billions of solar masses. Objects far too massive for the young galaxies they appeared to inhabit. Third, the sheer abundance. There were simply too many of them. Whatever they were far more common in the early universe than any existing model had room for. Each observation individually might have been explained away. All three together constituted what one research group described as a fundamental challenge to the standard picture of how black holes and galaxies co-evolved in the early universe. And then the spectra got better. Through 2024 and 2025, astronomers accumulated higher quality spectroscopic data on individual little red dots using JWST's NIR spec instrument. These were not just photometric signatures from imaging, but detailed measurements of how the objects emitted light at every wavelength. The kind of data that reveals the physics happening inside an object rather than just its appearance from a distance. What the highest quality spectra revealed in 2025 and confirmed in research published in Nature in January 2026 was something that resolved the central mystery while opening several new ones. The little red dots are young black holes. Not the supermassive black holes we know from the centers of modern galaxies, which have had billions of years to grow to masses of millions or billions of times our Sun. These are smaller, far smaller than previous estimates had suggested. Between 100,000 and 10 million solar masses, enormous by human standards, but relative pipsqueaks in the hierarchy of cosmic black holes. And they are completely enshrouded in dense cocoons of ionized gas. The gas cocoon is the key to everything. It is why the little red dots do not look like known active black holes. It is why they lack the X-ray signature. The gas surrounding them is so dense, electron densities so extreme they are barely physically plausible, that the X-rays the black holes are producing are absorbed before they can escape. The cocoon traps the hard radiation and reprocesses it. What escapes instead is the thermal glow of the dense gas itself, heated to extraordinary temperatures by the black hole consuming material at its center. And the physical details of what is actually happening inside these cocoons explain why this class of object had never been observed before, and why it could only exist in the specific conditions of the very early universe. The electron densities inside the cocoon reach approximately 10 billion electrons per cubic centimeter, at the boundary of physical plausibility for astrophysical gas. At these densities, the cocoon is essentially opaque to X-rays. The hard radiation the black hole produces cannot escape. Instead, it heats the surrounding gas to temperatures of tens of thousands of degrees, producing a thermal glow that mimics the spectrum of a stellar photosphere. not all astronomers are convinced the case is fully closed. A competing theory proposed in July 2025 offers a genuinely different interpretation for at least some of the little red dots that has not yet been ruled out by the available data. In this theory, the objects are not young black holes and gas cocoons, but something even more exotic: supermassive population 3 stars. Population 3 stars are the theoretical first generation of stars in the universe, formed entirely from the primordial hydrogen and helium produced in the Big Bang, before any heavier elements existed. They are predicted to have been far more massive than any star that forms today, potentially reaching millions of solar masses, and to have burned through their fuel in geologically brief periods before collapsing into black holes. The question of why the little red dots disappear from the cosmic record around 2 billion years after the Big Bang has a natural answer within the black hole star framework. As the young black holes consume their gas cocoons, the dense material that makes them red and bright is depleted. The cocoon thins, the X-rays escape, the object transitions from a little red dot into a conventional active galactic nucleus, the kind of quasar that astronomers have been observing for decades. The little red dots do not disappear. They grow up. They become the supermassive black holes at the centers of modern galaxies, including possibly the one at the center of our own. This is the deeper implication that most coverage of this story has not emphasized. The little red dots may be the answer to one of the most persistent problems in modern cosmology. For decades, astronomers have known that the supermassive black holes in the earliest galaxies JWST has observed are far too massive for their age. Under the standard model of black hole growth, a black hole forming from a stellar collapse cannot grow to billions of solar masses in the few hundred million years available before these early massive black holes appear. The timeline does not work. The growth rate required exceeds what was thought physically possible. The debate will not be resolved by JWST alone. The Nancy Grace Roman Space Telescope, scheduled to launch in mid-2026, will survey the sky 100 times wider than JWST's field of view, producing a census of little red dots across a far larger region of the early universe. That census will constrain the population statistics in ways that should distinguish between competing models. And the continued accumulation of JWST spectra, the telescope is currently generating data faster than the astronomical community can fully analyze it, will add to the sample of objects whose physics can be studied in detail. There are 341 confirmed little red dots as of 2025. The true number is certainly higher. Each one is a window into a process that happened 13 billion years ago, and whose product is sitting at the center of the Milky Way right now. Sagittarius, a star, the supermassive black hole at the heart of our galaxy, weighs approximately 4 million solar masses. It is quiet today, but 13 billion years ago, in the first few hundred million years of cosmic time, something very similar to a little red dot may have been the seed from which it grew. A young black hole surrounded by a dense cocoon of gas, consuming its surroundings at an extraordinary rate, glowing red and brilliant in an era of the universe that no instrument had ever been able to observe until 3 years ago. JWST did not find something that broke our understanding of the universe. It found something that may finally explain a part of it that was missing for decades. The first generation of supermassive black holes caught in the act of becoming what they are wearing a disguise that made them look like nothing we had ever seen. We had the evidence scattered across thousands of deep field images for 3 years. It took that long to understand what we were looking at. Now we think we know.